Signal conditioning on the inverting amplifier. If you look here to the top on the left side, you have here a circuit diagram of our operational amplifier connected as a inverting amplifier. If you look better at it, you can see that you have the input connected to the inverting input. That is, you're taking your signal into the input denoted with the minus sign, and that is the inverting input. And the other input is connected to the ground, the positive one, which is the non-inverting input of the operational amplifier. You have one resistor in the input line, and you have one resistor from between this negative inverting input at node X and connected to the output. This resistor is called the feedback resistor. And you have the input voltage, output voltage, and you have the current I1. Now, if you look at some notes about this inverting amplifier, we have that the input through the R1, the rest R1, which is in the input signal line, goes to the inverting input. We have the non-inverting input is grounded. We have the feedback through the resistor R2 to the inverting input. Here we assume some typical values for this operational amplifier, which is that we have the open loop gain at 100,000, and we say that the output voltage should give you some plus minus 10 volt, which is a typical limit. Depends on the supply voltage that you have. You have an input signal, which here is said to be very small or almost zero, where you have it is like 0.1 millivolt plus minus, and that's why we say that the node X is virtually at earth potential, because the voltage signal the voltage is so very low here at this node X. So there we say that we have a virtual earth potential. Now, if we look closely at this, then we can assume that we have a voltage drop over resistor R1, and we also have a voltage drop over resistor R2. If we look at the resistor R1 in the input signal line, we can say that this voltage drop must be the voltage input value minus the voltage potential at node X. And if we have in mind that the open loop gain for the operational amplifier for the ideal model would be infinite, and that the potential at the node X should be zero, then we can say that we allow ourselves to say that the voltage over this resistor R1 is equal to the input voltage minus 0, and thus we know that the voltage over this resistor R1 is equal to the input voltage. And if we use Ohm's law, we can say that the current flowing through R1 times the resistance R1 is equal to the input voltage, so that we can calculate it. Now, as mentioned before, the input impedance for the ideal operational amplifier should be 0, so that we assume that there is no current flowing through the node X into the operational amplifier. You should think of the equivalent model of the operational amplifier. This means that the total current through the resistor R1 also flows through resistor R2 as IR2. Think of Kirchhoff's current law for current division. If you look closely here, you can see that if you have the current flowing through R1 going into node X, and there is no current continuing into the inverting input of the operational amplifier, then all the current must be going through the feedback resistor to the output. And thus we can say that we know the current through the resistor R2, the feedback resistor, and that we can look at the voltage drop over this resistor. And we can say that because there is no complication with looking at what is happening inside the operational amplifier, we can say that we have the voltage at node X minus the output voltage should give you the voltage drop over resistor R2. And this is valid because we assume an ideal operational amplifier with the open loop gain of infinite and that the voltage at node X is equal to 0. Then we can say that the voltage drop over resistor R2 is equal to 0 minus V out, or the output voltage. That is, if you look at this original equation and remember that, and then you can use Ohm's law and rewrite the equation where you have the current I1 times R2 equals to the negative voltage on the output, because the inverted signal on the output. Remember that we said that all the current that goes through R1 must be also going through R2, so that the currents must be equal. And so you can allow yourself to write that it is I1 or IR1 that goes through the resistor, and use Ohm's law to calculate it this way. So with this in mind, we can continue and remember the general model for the amplification or the gain of an amplifier. Then you can say that the general model says that the gain is equal to the output voltage divided by the input voltage. And so if we use the two previous equations that state how to calculate the output and the input voltage, you end up with an equation that says that the gain is equal to the negative ratio between R2 and R1. Now note that here I write A to denote that we are talking about the voltage gain. In some literature you might see that it is denoted with G, and also in some other notes from me you could see that I might write it with a G somewhere else, but both are valid denotions. Another thing, the negative sign indicates that the output is inverted, that is, it's 180 degrees out of phase with respect to the input voltage. So when you have an inverting inverter, this is what it means. It inverts the input signal 180 degrees out of phase with respect to the input. Let's try and calculate a simple example showing or applying what I've been talking about. If you consider an inverting operational amplifier where you have the resistor R1 equal to 1 megohm and the resistor R2, the feedback resistor, is equal to 10 megohms, then what is the voltage gain of the circuit? Well, you use the above equation, this one, and calculate the ratio between these two resistors. Then you should have the answer that the gain is 10 times, or negative times 10. Now, it's always fun to have some application examples or idea of how or where to use such a circuit. Such a circuit could be used to convert current to voltage. If you think about that, you can use a reverse biased photodiode in place of the resistor in the signal line for R1, and that the photodiodes are widely used sensors that give small currents when exposed to light. Then the output of the amplifier can be used as an input to a microcontroller, looking at this where you have the change in current having a changing voltage signal on the output that you can send into the microcontroller and analyze. I have here another problem or example to help understanding with calculating this. Well, if you have problem 1, you have to design an operational amplifier circuit that can be used to produce an output that ranges from 0 to -5 voltage when the input goes from 0 to 100 millivolts. Now, to find the answer for this, you have if you look at the original diagram, you use this circuit here, where you have on the input you want to have 0 to 100 millivolt. On the output you want to have -0 to -5 volt out. This means for us that we go in and say that the ratio between R2 and R1, or the output and the maximum output voltage and the maximum input voltage, should be equal to 50, and then you can calculate that or determine or select that the resistor R1 should be 1 kilo ohm, and then you can calculate the size that you want for the feedback resistor R2. Another problem is if you have an inverting amplifier with the input resistance of 2 kilo ohms, and you should determine the feedback resistance needed to give a voltage gain of 100. So you say that if you have the resistance in the input line is equal to 2 kilo ohms, and we use the previous equation, then you can use that or convert it so that you have that the feedback resistor is equal to 200 kilo ohms. And this sums up an introduction to the inverting amplifier and how to do some simple calculations for it.